Hi, my name is Aaron Kimball. I'm the Chief Architect of Weeby Data, and we help organizations build big data applications. Today, I'm going to talk for a little while about data science and how it relates to big data, and specifically what kinds of tools one would want to use to manipulate big data beyond MapReduce. Data science is often about modeling, and models predict the future. There's several ways that models can predict the future. For example, they can predict the future about how a business is going to perform. What will be the supply and demand of that business's products, or what might the prices do of the raw materials they require? Models can also predict the future about individual users or customers. For example, you can make predictions about a product that an individual customer might want to purchase, or a user on a website might want to see some particular piece of content next. Modeling the business is something that we've been doing with data for a long time. This is often referred to in other contexts as business intelligence. Business intelligence often involves summary statistics or reasoning about how a large volume of data can be condensed into a smaller report to be used by individuals who make business decisions. For example, you might look at where the traffic to your website is coming from and use that to alter where your marketing budget will be spent to drive more traffic more effectively in the future. When thinking about using Hadoop to model the business, you might look at a few different tools. MapReduce is the workhorse of a lot of Hadoop-based computation. There are other systems like Hive or Pig, which are higher-level languages that can write to MapReduce and run MapReduce programs, or another tool such as Impala, which allows you to run SQL queries over Hadoop. Modeling individual agents, customers, or users is a different kind of modeling. Confusingly, this is often referred to as predictive analytics, even though we're really predicting something in both cases. But predictive analytics often uses the kinds of algorithms that we think of as machine learning: classification, clustering, regression, or collaborative filtering. When we think about how to model agents, we have to take this data and split it out or condense it along a number of different dimensions. For example, all of the records pertaining to an individual user need to be considered together. We also need to slice things by the kind of feature that they are, and we also involve a heavy time series component to this information. It's often more important to understand how tastes or preferences are changing rather than to look at a total global snapshot of tastes as an average at a point in time. When thinking about how to store and process large volumes of data, one technology component stands out head and shoulders above all others today, and that's Apache Hadoop. Today, Hadoop and big data are nearly synonymous with one another. Hadoop allows you to store web-scale data, data sets that are themselves about the same order of magnitude of size as all of the content on the World Wide Web itself. Many machine-generated data sets, or data sets that contain micro-observations about large populations of individuals, can approach this web-scale size. Hadoop itself is broken out into a number of components, and many more components form a larger ecosystem around Hadoop. But for this discussion, I'm going to focus on the two core components of Hadoop, HDFS and MapReduce. HDFS, or the Hadoop Distributed File System, is the main data storage location for web-scale data. HDFS is often referred to as a data lake. It's a repository that is built on top of commodity hardware that can scale out in an inexpensive fashion and can reliably store terabytes, petabytes, or more amounts of data. The kinds of data that can be written by a web application or another system such as a web crawler into HDFS represent logs of activity in that application, user behavior, third-party data such as inventory forecasting or marketing analysis, as well as unstructured data such as the contents of email messages to a support address, forums, or other web pages. For example, you might crawl another site and understand the product catalog shown therein. HDFS by itself doesn't do any computation. That's what MapReduce is for. If HDFS is a data lake, MapReduce is often referred to as a data refinery, taking this vast amount of information and refining or distilling it down into a smaller amount of information in the form of a report, spreadsheet, or chart that people can actually act upon. MapReduce is a batch-based system for performing analytics. This has pros and cons associated with it. The batch nature of MapReduce means that it's very easy to do computation over heretofore unseen volumes of data at a time. If the input data set to your process is a petabyte of information, MapReduce can still do this, possibly employing maybe 1,000 computers at a time to do the heavy lifting. But in order to operate at this large scale, MapReduce has some overhead built into it. MapReduce doesn't scale down particularly well. It would be a really inefficient use of resources to use MapReduce to compute over hundreds or thousands of records. You're looking to use MapReduce when you have billions of input records or more. This puts a lower bound on how frequently MapReduce jobs can run. MapReduce jobs can probably run at most about once every 30 minutes. And more realistically, organizations often run a MapReduce job overnight, or maybe 2 or 3 times in a given day. Another piece of the puzzle here is that in a MapReduce job, the data set which forms the input to the job needs to be defined ahead of time. This is in contrast to how the data set is actually being formed. For example, if you're recording logs out of a running web application, this log file will be continuously written to. But at some point, there's a cutoff, and the data that's there prior to the cutoff is what's considered as input to the MapReduce job. This means that MapReduce can't really do streaming or incremental analytics. MapReduce jobs always think of a large partition of information. For example, all of yesterday's data or all of the data for the last several months in some data set at a time. MapReduce jobs are especially helpful for modeling the business. For example, a marketing organization might want to look at the web logs to their website, which might be a very large amount of data, in determining their marketing spend. MapReduce also plays a role in modeling individual users, but this is a little more complicated. How you consume models of users is very different than how you would consume models of a business. If you have actually used a website like Facebook, LinkedIn, Netflix, or Amazon, you've actually interacted with a model of yourself being reflected back to you by this site. For example, LinkedIn uses tools like MapReduce to help compute the people you may know function in order to discover more connections for you. Facebook uses tools like MapReduce to gather prioritization for what data should show up in your news feed if you have a very large number of your friends. Netflix uses machine learning and predictive analytics to come up with models to show what sorts of movies you might want to watch next. And Amazon uses this same sort of technique in order to suggest products that belong in your shopping cart. A key distinction between modeling the business and modeling users, though, is timeliness. Tools like MapReduce and HDFS have been proven in the marketplace for a few years now, and they're becoming adopted in a lot of places. But as I said earlier, MapReduce is pretty slow to respond. If you're running a model overnight, that means that that is the greatest frequency with which you can produce more relevant updates to an individual user. As you yourselves probably know, if you shop on Amazon, the kinds of things that you might want to purchase on the weekend might be very different than the kinds of things you want to purchase next Thursday. If it takes between the weekend and next Thursday in order to come up with new recommendations for you, then those recommendations are going to be out of date. We want to respond to users in real time. We want to understand a global model of how all of our users might interact with our site, and then score this model against an individual user while they're in the same session. We want to respond to their actual preferences at a particular moment in time. Timeliness is very important to relevance in modeling individual user agents. In order to produce recommendations and serve them back to users in real time, we need to look to additional components than just HDFS and MapReduce. We need to start thinking about a more holistic big data application. A big data application is something that is a web or a mobile app that observes how its users interact with it. It tracks as much of this behavior as it can and uses that with the expertise of a data scientist to produce models of user behavior. These models are probably trained using something like MapReduce so that they can cover a large number of users and a large historical record in building the model itself. We would then respond to users interactively by doing a rescoring of that model against their particular profile in real time. And then we need to serve this model back to them using another real-time storage platform. The one that we like to use is called Apache HBase. HBase is a NoSQL key value store like Cassandra, MongoDB, Voldemort, or one of several others, which enjoys particularly close collaboration with the Hadoop project. It's easy to use MapReduce to iterate over data stored in HBase, and you can use HBase to provide the scale-out functionality needed to power a large website. Facebook Messages is powered by HBase, amongst other applications. At WeBeData, we've taken HBase, MapReduce, and some other elements and used that to build a big data application server that we call Kiji. A big data application server is to machine learning models and user profiling as a web application server is to building a modern website. You'd be insane to actually start from scratch and write a web server and build your application directly on top of that. Similarly, it's a lot of work to go directly from raw Hadoop MapReduce to building a web application which is interactive and personalizable. Kiji helps you bridge that gap. It's built in a layered fashion, and at the bottom of this layered stack are HBase and MapReduce and HDFS, like I've spoken about earlier. We also include another Apache project called Avro in this level for data serialization. On top of that is something that we call Kiji Schema, a schema management layer which manages the tables of information that one would store in this system. We have a number of ways that users can interact with Kiji for computational purposes. KijiMR helps Kiji applications talk to MapReduce. A Kiji Hive adapter gives you access to Hive, which is a SQL layer for MapReduce. And Kiji Express is a new system that we use for helping data scientists get access to this information in an interactive environment. We have a REST server, which will allow a front-end application to interact with this big data backend, and the Kiji scoring server, which can take a trained machine learning model and serve that in real time. Data scientists would interact with Kiji using a workflow like the one shown on this slide. There are several large coarse-grained steps that a data scientist would take in training a model to personalize a web application. In the preparation step, you'd start out by preparing any auxiliary data sets that are required for training a machine learning model. Lookup tables, for example, or the ability to relate user IP addresses with geolocation data. Next, you'd define an extraction function which takes a raw data record from the input data set and converts that into a feature vector. Part of the data scientist's job here is selecting good features. These are then fed into the training step where you train the model itself, whether that's a classifier, a clustering algorithm, collaborative filtering, or some other representation. This trained model would then be used as part of a scoring function. You'd take an individual user's input data, again, run the extraction function over it to convert that user into a feature vector, and then you would use that trained model in conjunction with the feature vector in order to produce new recommendations or profiles for the user. In the last step, we evaluate the model and determine whether it's better or worse than the model that we might have used last week. This slide shows how you might apply models in real time. As shown here, there are two different workflows in play. One of these is the batch process, and one of these is the interactive process. Data scientists themselves would more directly interact with the batch aspect of this, exploring data sets, training new machine learning models, and then validating these trained models against historical information. The output of these trained data sets would be stored in locations that we call key value stores, shown here in green on this slide. These key value stores can be loaded into the scoring server, which would score a trained model against individual records representing the behavior of particular users. The scoring server is used only when a particular user logs into the website and needs new recommendations, so these recommendations are always up to date. To wrap things up, modern web applications are turning into big data applications. They observe how users interact with them and personalize and tailor the content to provide a more relevant, timely, and powerful experience for the users. Data scientists use their particular insight and business domain expertise to produce better recommendations and more responsive applications. If you want to try Kiji, it's open source, and so I urge you to check this out. It's at kiji.org. And if you think this sounds cool and you want to help build systems like Kiji, come to jobs.webedata.com. We're hiring. My name is Aaron Kimball, and I'd like to thank you for listening. If you've got any questions, please send me a line at aaron@webedata.com.